In the last screencast, we saw that for ideal gases, we could develop this relatively simple expression for the delta G of mixing, that it was dependent on the total number of moles and the mole fractions of the things that you were mixing together. So if we had two gases, we'd have these two terms, and this was good for ideal gases mixing if the initial pressures were the same and they were mixing at constant temperature. And you probably thought, well, this is very nice, but I do my chemistry in the liquid phase, right, in solution phase. And so what use is this thing for mixing gases? Doesn't seem very significant. Well, actually, it's very significant because we can adapt it to solutions with just really, we can adapt it for something called ideal solutions, and later on, with this a small little twist to it, we'll be able to adapt it to all solutions. So how do we do that? Well, first, let's look at what the enthalpy and entropy of mixing are for gases, and then we'll look and see if there are any solutions that have the same characteristics. So first, let's look at the delta S of mixing for ideal gases. Okay, so for now, we're still talking about the ideal gases, but I'll show you later how we can adapt this to the solution. Okay, so what we can do is say that we know that if we take the partial of the Gibbs energy with respect to temperature, that's equal to the negative entropy. And we could also say this for changes in Gibbs energy. So if we look at the partial of the delta G of mixing, I forgot to write mix in there, there we go, delta G of mixing with temperature, that should be equal to the negative of the delta S of mixing. Okay? So this is just something we got from the differential of the Gibbs function, and here we're saying we're just adapting it to changes when we mix. Well, this tells us we have this expression up here for delta G of mixing right up here. Why don't we just take a differential of that a derivative of that with respect to temperature? Okay, so the derivative is going to be equal to, let's go ahead and do this for this equation up here with respect to temperature. Well, let's see, we've got, we're doing this at constant, we should say all these are at constant pressure. Okay, and because we could also change the moles of A and B, let's go ahead and say that those are being held constant too. All we're changing is the temperature. Okay, now that we can change moles of A and B, we actually have to include those as things that we're not changing. Okay, that's supposed to be an N. Okay, so take derivative of this expression up here. Oh, this expression's wrong. What did we leave out? We left out RT. Okay, now it's right. Now let's go ahead and take the derivative of this, and we see N is a constant, R is a constant. We take derivative with respect to T, so we end up with 1. And all this in here in parentheses is also a constant. Okay? And so we get x a log of xa plus xb log of xb. And if we had other components, if we had more components than just 2, we would just have more terms. And we mustn't forget this negative sign here, so let's put the negative sign up here. Okay, notice this is what tells us. This tells us that since mole fractions are less than 1, this is negative, and this is negative, and so this whole thing's negative. So delta G of mixing is negative, and so ideal gases mix. Okay, we already knew that. So what does this mean? This means that as they mix, well, these terms are negative, right? Because they're logarithms of things that are less than 1, so this whole thing's negative, but then we're multiplying by a negative, so this means that delta S of mixing for these ideal gases is going to be a positive number, okay? The entropy of the gases go up when they mix, and that's probably intuitive. So we've got two equations now for mixing ideal gases. We said delta G of mixing was going to be nRT, and then this xa log of xa, xb log of xb term. And delta S of mixing, we said was going to be negative nR, because we took a derivative with respect to temperature, xa log of xa, xb log of xb. Okay, great. Well, we can use these to find the enthalpy of mixing. So we know that delta G is equal to delta H minus delta T times S. And if we were working at constant T, which we were, right? These expressions were for constant temperature mixing, then we can say delta G is equal to delta H minus, well, we can pull the T outside since we're at constant T. So T delta S, and that's an expression you're familiar with already. And so we can say delta H is just delta G plus T delta S. Well, we have delta S of mixing, we have delta G of mixing, so we can use that to get delta H of mixing. So delta H of mixing, we said is delta G, this expression up here, minus T times that expression there. And I think you can see what's going to happen. We get nRT XA log of XA plus XB log of XB. And then we're going to add T times delta S. And so we add, here's delta S, but we have to multiply it times T, XA log of XA plus XB log of XB. And you can see what's happening when we add this up. And I forgot something. I forgot that delta S has a negative sign. I better put that in there. Okay, so when I add those together, what's going to happen? They're going to cancel. And we're going to get delta H of mixing for ideal gases is equal to 0. And let's go ahead and just point out that we're talking about ideal gases still. Okay, so thermodynamics of mixing for ideal gases is that we have this positive entropy term and we call athermal mixing. Just means that it's not exothermic or endothermic. There's no heat released or gained. And if we have athermal mixing and we have a positive entropy change, then we know that there is going to be a negative delta G. Okay, great. So looking at this, we can see mixing of ideal gases is driven by entropy and is spontaneous, right? Because our delta G at constant temperature and pressure is negative. Okay. Now we have to ask, is there any way we could apply this to solutions? Well, let's see if we can. An ideal solution, we could define it this way. An ideal solution would be one that has a delta H of 0, delta H of mixing of 0, and a delta S mixing of negative NR XA log of XA, XB log of XB. Well, in other words, we're defining an ideal solution as one that has the same oh, I forgot the S over here. There we go. That has the same thermodynamics as mixing ideal gases. Well, is that realistic? Well, it turns out it's very realistic if you meet these three conditions. Okay? So it turns out you will get this if things mix randomly. In other words, we know that if we mix helium and argon, because there's no interactions, they mix randomly. The distribution of helium atoms and argon atoms in an ideal gas mixture, that they're totally random, right? Well, when would we get this in solutions? We get this in solution if we have these characteristics. If we have the same size molecules and the same shape of molecules. Okay, so they can pack the same. And also, if they have the same IMFs, the same intermolecular forces. Now notice we don't have to have no IMFs to have random mixing. Okay, if we have a beaker and I've got, and this is way not to scale, okay, but imagine I have some hexane, let's say I have cyclohexane and I have cyclopentane molecules. So they're roughly the same size and shape. We know that the interactions between these two molecules are van der Waals interactions, actually London interactions specifically, and between these two is London. So if we allow them to mix so that we have you know, in some cases we've got unlike together, and in some cases we've got like together. Okay, something like this. If we allow them to mix, what we've done is replace London interactions and London interactions with London interactions. In other words, we've made intermolecular forces that have the same energy or enthalpy as the ones that we've broken. So we can say that the unlike IMFs are equal to the average of the like IMFs. Okay. And of course this is approximate, but for it to be an ideal solution, this would have to be actually exact. So this is the unlike IMFs, and this is the like IMFs. Or this is the self IMFs, and this is the non-self IMFs, probably a better way of saying it. Well, if they're exactly equal in strength, you don't gain or lose enthalpy when you go from mixed to unmixed or vice versa. And if this is true, if that's true, then it must be that delta H of mixing is equal to 0. Okay? So ideal gases have a delta H of mixing of 0 because there's no IMFs. So you're replacing no IMFs with no IMFs when you mix. But when you have an ideal solution, you're replacing IMFs with IMFs of equal strength. As long as they're at equal strength, it doesn't matter whether they're strong or weak. Okay? And so if this condition is met, the same IMFs, or equal in strength IMFs, and usually that means the same type of IMF, then delta H of mixing will be 0, and you'll have random mixing. And if you have random, and also the same size and shape, you'll have random mixing, and if you have random mixing, you'll have the same entropy generated when you mix, and your thermodynamics will be identical to ideal gas mixing. Okay? So let's go ahead and just look at ideal solutions. Do we ever see something like ideal solutions? Yes. Well, we can imagine, what about, these are ones obviously that are near ideal. They're not perfectly ideal. What if you had methanol and ethanol? Okay, so you've got two hydrogen bonding solvents. They're both alcohols. They're roughly the same size. Ethanol's a little bigger, of course. That'd be pretty close to being an ideal solution. What about decane and nonane? So you've got a 9-carbon, and a 10-carbon hydrocarbon that are both linear. Okay, same size. They're both long molecules. They're both held together by the intermolecular forces are London forces. So yeah, that would be an ideal solution. What about the classic one is benzene and toluene? Okay, so this is perfectly circular, and this has a little bump on the edge, but they're both plate-like molecules. They're both aromatic. They're both held together mainly by London interactions. Although there's a type of quadrupole interaction as well. Yeah, so same IMFs. Okay, same size and shape. And finally, this one that you might not have thought of: silver and gold. And so all of these at room temperature are liquid solutions, right? You can mix them in any proportions, and they'll just spontaneously mix in. They have a delta G of mixing of that's negative, just because, and it matches the expression we saw earlier. But this would actually be something called a solid solution. So if we look at the radius of that says solid. Okay, solid solution. If we look at the radius of a silver atom and a gold atom, they're not that different. They're both transition metals in about the same part of the periodic table. And so their properties are very, very similar, and so they can replace each other in the crystal lattice that they form in the solid. And so we can vary the composition continuously without forming. There's no crystals of gold and crystals of silver. They're mixed in evenly. It's just that it's a solid, so it's called a solid solution. And we'll see later when we look at the phase diagram of silver and gold, it actually is very, very close to an ideal solution. Okay? So the thermodynamics of ideal solutions, just to refresh your memory, delta G of mixing is going to be the same as for gases. nRT XA log of XA, XB log of XB. The entropy of mixing is going to be negative NR, but then what's in parentheses is the same. I'll just put ditto marks in there. Okay. And the delta H of mixing is equal to 0. Chemical potential varies with composition. So we had delta G mix is equal to nRT XA log of XA plus XB log of XB. If we take the derivative of that, we know the derivative of the Gibbs function with respect to number of moles of A is equal to the chemical potential of A, and that's constant temperature and pressure, and moles of B, C, D, etc. We could also do the derivative of the delta G of mixing with respect to number of moles of A, constant T, P, number of moles of everything else. And that would give us how much the chemical potential changes with mixing. And if you take that derivative, and it took me a couple pages of algebra, so I'll skip that and just give you the result. If you take this derivative, you get that delta mu of mixing for an ideal solution is equal to RT log of the mole fraction. So that's if we're talking about the chemical potential of A. And so if that's how much the chemical potential changes by, we can say the chemical potential of a component in an ideal solution is equal to the chemical potential of the pure component plus that delta term, plus how much its chemical potential changes when it is mixed. So remember, this is the chemical potential for something that's in an ideal solution.